Hey class, Adam Ward here. I want to talk with you about the Streeter-Phelps equations and how we can deal with distributed sources of deficit and biological oxygen demand, as well as actually distributed sources of oxygen or DO into the system. This goes along with Chopra's lecture 22, and what we're basically going to do in this lecture is make our Streeter-Phelps equations even uglier. So let's do it. We're going to work on three ways that you can represent distributed sources, and in all cases these will be no-flow sources. So you've got to picture sources of DO or deficit that don't have any discharge associated with them. These might be described to you in one of three ways. The first being volumetric. That's a capital S with a lowercase d in this case to denote distributed. And later through the chapter, Chopra replaces that with an L if it's a source of BOD. So that SD will turn into an SL at some point in your life. These could be aerial loading. So this might be something like atmospheric deposition. So how many grams per square meter of surface area per day? Or what Chopra calls line loading, how many grams per meter of stream per day? So SD, SD prime, SD double prime. We're in SD soup right now. These are easy enough to tell apart because those units on the bottom that I've circled in red here. Volumetric, you've got a volume on the bottom. Aerial, you have an area on the bottom. Line sources, you have a distance on the bottom. These can all be related to each other using geometric relationships that we've developed earlier in class. These are in your textbook in lecture 22, as well as here. Ways that you can convert between volumetric and aerial, volumetric and line, or aerial and line. So all of the terms that I've written, 5 of them in total here in black, are all equal to one another. So there's 3 ways that you might get these numbers. How do we incorporate them into our Streeter-Phelps model? So first, let's take a look at sources of BOD, biological oxygen demand. And again, this is a plug-flow reactor with a distributed source of BOD. So here's our typical plug-flow reactor equations. We've got the advection term minus U dl dx. We've got some sink term minus KL. And now we've got a source term plus SL. So that's that mass per volume per time in this case. And if we solve that equation for BOD, we can get exponential growth, basically a solution that looks an awful lot like a step load. Now, I've expressed this as BOD through time. Again, if you want space, you simply replace that, the t with an x over velocity. So this is a step load that will grow into some steady state, and Chopra gives us the steady state as just the coefficient out front, that SL over KR. So this is what we'll get for a distributed no-flow source of biological oxygen demand. There are similar equations in your textbook for deficit. I won't go through the equations here, but I want to talk conceptually about what happens, because this looks a little different than step loads we've seen in the past. So for deficit, if the only thing we have is a step load, we would get this exponential decay of oxygen down to some steady state level. Of course, we know the Streeter-Phelps model has this sag response to it, in which we get sort of this nonlinear, non-exponential behavior. That's a trade-off between reaeration rates and decay rates. And so when those two are added together, you get this total response curve, which has a kind of a funky shape to it. Now, because you've got both the sag response and the step load response, the actual equations that describe this are a little bit uglier. That's not to say they're anything we haven't done in the past. It's an explicit solution. You just plug and chug through it. But I won't go through writing those here. You can grab those out of your textbook if and when you need them. And just like BOD reached some ultimate steady state or constant rate level, you'll get the same thing from distributed deficit. So textbook equation 22.9 will give you how to respond to a distributed source of BOD for deficit. So you should check that out and add that to your notes to make them complete. Now that was the deficit side, or excuse me, the BOD side. When we deal with deficit, that's really about oxygen balance. And so we've already done reaeration. What other sources and sinks of oxygen can we imagine? And in fact, there are several. So if we write this equation out, you'll notice that I've added 3 new terms to the mass balance for this plug flow reactor for deficit. A P, an R, and then this SB prime over H. So let's talk through each of those briefly. P and R are describing photosynthesis and respiration. And so this is a volumetric rate, mass per volume per time. And what we're essentially accounting for here is that within the water column itself, you may have plants, algae for example, that are photosynthesizing and that are releasing oxygen into the water in dissolved form. You may also have respiration occurring from microbes that are living on those plants or by other species in the stream. And so that's a mass per volume per time as well. So photosynthesis, respiration, we can add in as simply as that. This SB prime, so you see that single prime, you're thinking in aerial rate, grams per area per day. That's a sediment oxygen demand. And so one of the things that we know happens in streams is that the water flowing in the stream is interacting with the stream bed. And we know that we've settled out some of that BOD as we move through the system. It settles onto the bottom, and we actually develop sort of a layer of BOD. So as water is flowing over it, that BOD on the bed is still decaying, and it's still stripping oxygen out of the water column. And so this SB prime term is sort of what happened to the BOD that settled. And it's not gone from our lives. It's still got to be dealt with. It's still going to decompose. It's just not stripping. It's just accounted for in the water column in a different way here. Okay, so we've got lectures 24 and 25 in your textbook. We'll deal with these terms more explicitly. So for the moment, we're just going to trust that they can be described as rates, and we will talk about what controls those rates later. And if we take this, and this doesn't affect the BOD term, right? Because these are sources and sinks of oxygen. So they have nothing to do with BOD. They're only affecting the deficit equation. And so the explicit solution for this, deficit through time, looks like minus the photosynthesis rate plus the respiration rate plus that sediment rate over depth divided by the reaeration rate coefficient Ka times 1 minus e to the minus Ka t. Okay. So now we've done distributed BOD, and we've done distributed oxygen, or deficit if you will. Let's plug this all together, and what we end up with is the total Streeter-Phelps model. Noting here that there's still no flow from these sources, so these are sources that don't put a discharge of water into the system. So 2 equations on top, the solution for BOD, on the bottom, the solution for deficit. Chopra has this in the textbook as well, but I want to just walk through it so that we're very clear on all of this. So the 2 terms that I've highlighted in red, those are your point source BOD. So those are what we did last lecture in class. We came up with this exponential decay of BOD and these competing rate laws that describe deficit. What I've circled in orange is what we started this web lecture with, distributed BOD. So that's showing up both in the BOD equation and in the deficit equation. In blue here, the distributed deficit, so that's what we did on the last slide. And that's only showing up in the deficit equation. And then that very first term in the deficit equation, again, that's the general solution piece. So that's any deficit that we had basically at the beginning of the segment that we're trying to model. So after this lecture, you ought to be able to take these total Streeter-Phelps model equations and adapt them for your system of interest. You've got a system with no point sources of BOD, take the red terms out. You've got a system with only distributed deficit, keep only the blue terms. So these equations are meant to be large, they're meant to incorporate all of the different processes, and then as you need them, you can simplify them down and only keep the terms that are applicable to your problem. We'll practice working on this in class a little bit and talk about how we can apply this to more complicated systems to account for all the point sources and distributed sources that we might come across. Thanks for sticking with me, and I'll see you all in class.